Hello guys, this is Sumit here. We'll be doing chapter 12, inventory management, from the 12th edition of operations management by Heiser, Render and Munson. In the inventory management, there are a couple of concepts that we're going to cover today, especially the one that deals with numerical problems. The first one being the ABC categorization of the inventory. Let's see. So in the classic ABC analysis, we want to find out the topmost selling category, the medium, and the low annual by the dollar value of the volume of the product sold. Okay, so depending on what author or what book you're using, roughly the categorization is 70%, 20%, and 10% for the A, B, and C category. So if you were to bring in all the things in the inventory in the dollar values only, such that they can all be comparable, because otherwise you might be dealing with pounds of salt or ounce of salt versus garments. So it's difficult to compare them, but we are trying to bring them all in the dollar values. That's the key here. So and there's a roughly, it's not a hard and fast rule like it has to be exactly 70%, 20%, and 10%, but that is the idea. I mean, it could be somewhere between 70 to 75. The next one could be 16 to 20, and then the last one could be the leftover. Okay, so in going through that, let's take an example of the end of the chapter problem 12.3, when we are given the data for some of the items that are sold at the restaurant. Okay, now the first thing to do is we are given the dollar value per case and the number of orders placed per week. Okay, so the first thing that we want to do is to calculate the dollar value for the whole year. Okay, so the first thing we want to do is, given the dollar value per case and the number of orders per week, if you were to multiply these, you will get the dollar value for all the orders for that item per week. Now also, if you were to multiply this value by 52, because there are 52 weeks in a year, you will get the annual dollar value for an item. Okay, so let's do that. First, we're going to calculate the dollar value per week. Now this will be the total. So 3 times 135, yeah. Also, if we were to say annual dollar value would be this times 52. Okay, and let's bring that in as dollar values. Yeah, okay, and this is good enough. Now based on this, let's calculate the ranks, respective ranks. So I'm going to use rank this in the range this, which I need to freeze, comma, ascending or descending. Okay, I'm going to use ascending first. Let's see if it works, and copy it down. Now at this point, I'm going to select all of my data set and use filter, and then sort all of them by ranks. So currently this is giving me the lower value, so I should have been using the descending. Okay, now let's try that again, smallest to largest. Okay, now that sorts all of our items based on the highest dollar value as the lowest rank. Okay, now the next thing we want to know is the percentage. So let's say now we know that fish fillet is ranked number 1, but what percentage of the values is it compared to the total? Okay, that's what we want to know. So let's say the percentage for this is the individual value divided by the sum of all of these. I'm going to freeze it so then I can use the same formula. Oops. Yeah. Okay. Then I'm also going to say, let me bring them as the percentage with 2 decimal points. Now, at this point, when these are all sorted, okay, I'm going to say cumulative percentage, which is equals to this value, and then the current value plus the previous value, and I'm going to take it all the way across. Now, if everything is working fine, the last value of cumulative percentage should be 100%. This should be taken as running total. So if you were to say the fish fillet only is 17%, French fries alone is 16%, but if we were to take the cumulative percentage of French fries plus fish fillet, that is 34%. Now the cumulative percentage at up until this point 70%. Now this is 69% here. So you were to say the first 6 items alone contribute 78% of the annual purchase. Yeah. So now you can categorize all these as A items, and then start for B items for the next 20%. Let's say I would stop here at 95% or so, or even start saying C, C, C. All these items would be C category. Yeah. So you can see the number of items that contribute majority of sales are very fewer. The number of items that contribute very little, but there are too many of them, that's the category C, and anything in between is category B. Okay. So let's categorize that. As A, and then maybe B, and then C, okay. Now at this point, if I wanted to show this on a compact form, now for what is the annual dollar value for all 20 items? Since I calculate this in the denominator here, let's calculate for the part A equals to some, yeah, I don't need this. Excel trying to be smart. Okay, so this is the dollar value. What are the C items? The C items would be these. Okay. So these are the C items. You can name them: eggs, oil, trash can, garlic powder, napkins, and so on. What's the most expensive item using annual dollar value? So this would be fish fillet. Okay. Now also, if you wanted to show this on a bar chart, then first I would make a small table: category A, category B, category C. Now category A as a running total, this is the last value here. B, this is the last value here. And then the C, of course, is this last value here. Okay. Now this is from the cumulative value. In order to for us to show the various bins, I'm going to say this equals to this, and then the category B alone is 95.78, yeah, and similarly category C alone contributes to 4.29%. Also, if I wanted to project the numbers in addition to the dollar volume, now this is percentage, and this is number of items. I can say count okay, and then count or why don't I do this equals to count if freeze it, comma this guy here, such that I don't have to do manually, and I might be wrong there. So what I've done here is count if in this range is equals to this value here. So if it's A, then it counts them as 6. If it's equals to B, then it counts them as 5. So as you can see, it counts everything in this range if there is anything matching to C. Okay. So now with this, we can make a bar chart easily, wherein this is the percentage in the blue. So first thing, I'm going to say add data labels, add callouts, and then this one I'm going to say format data series and show them on secondary axis. Okay. Still not what I was looking for. Let me change the graph here. Change the chart type, combined. I want this to be, let's say, the line graph. Okay. Somewhat better. Okay, so in terms of category, we have category A item 78%, B item 16%, C item is 4.29%. In terms of number, category A item makes up so these are represented on this axis. Yeah. Similarly, this one over here, and this is represented on this axis. Yeah. So number of items for category A are very few, B are also very few, and C contributes so many of them. Yeah. Another way, if it's not very clear, this is just FYI, not even asked in the question, but let's say if you were to say, how do I get rid of this? Okay, better. You can also present these instead of number. You can say percentage of number of items. You can say this divided by count of all the numbers. Make sure you freeze them. Oops. Let me try it out here. Count no, it's not going to count. Let me. So it's looking for the numbers. So let me give it the numbers. Count all of these. Now, by the way, we are already given the number of items here, so you can either use that, but just kind of feel that why is it not working. So this one also, and then end. So there are 20 items. So if I was to say this divided by 20, I'm going to show these as well in the percentage terms. Yeah. So now if you were to say that 30% of the item account for 78% of the dollar value, then 25% of the items account for the next 16% of the dollar value, and the 45% of the numbers account for only 4.29% of the annual dollar value. Okay, so this is how you can do how you can categorize the items in the inventory as category A, B, and C. All this helps is drive the focus of, let's say, if you're a manager, on the things that are more critical or the things that are more important for you in terms of the money. It may so happen if you're working, for example, in this case, a restaurant, even though category C accounts only for 4.29%, but some of the items might be critical in nature. When I say critical in nature, I mean, some of the items that you cannot, a business cannot be run as usual. For example, let's say without the eggs or oil, none of the other dishes can be made. However, it could be critical in nature, but in terms of dollar value, this does not amount to a whole lot of your expenditure annually. Okay, now let's move on to the next type of questions that are there in the inventory. The next important concept that we have here is, let's say, inventory usage over time. We have something called economic order quantity. There are a few assumptions for the economic order quantity. However, the basic key point is that it minimizes the amount you will end up spending in ordering versus storing. Okay, so, and that is notified by this graph, wherein if you see that if you were to plot in your holding cost, it goes on linearly. Okay, so the more you store, the more cost you have, and for any given amount of time, let's say if you were to increase the number of quantity here, then your cost goes up by this much percent. Similarly, if you were to do the same amount of quantity of increase, about this much, then you will have the same amount of increase. Yeah, so for same amount of increase in quantity, you have proportionally same amount of increase in the cost. However, for the storage, every time you increase even though the same amount of quantity in terms of ordering, you end up reducing the cost of storage less and less. Okay, so for this amount, your cost went from here to here, so you're talking about a decrease of this much. But when we went for the exactly same more amount in terms of storage, you only reduced your cost by this much. So this is called reducing the cost at a decreasing rate. Okay. However, at a point wherein both these holding cost and ordering cost intersect, that is termed as EOQ, okay, or optimal order quantity, Q star. This is given by 2 times the annual demand. Now remember, this has to be annual demand. Okay, 2 times D times S divided by H, where this is annual demand, this is setup cost or ordering cost per order. Okay, and this is holding cost for 1 unit of storage per year. This is, okay, how much it costs to store 1 unit for a year. So the units are very important, okay, and the whole thing has to be taken the square root. Okay, so this is how we calculate the EOQ. At this point, the ordering cost and holding cost would be exactly the same. Now, one more key takeaway point is that in this one, let's say when the time goes by, let's say from, it could be for the same period, let's say 1 to 10 days, and then again 1 to 10 days. If the inventory is shows up on the day 0 at beginning of the time period, there is no breakdown time. So if the wholesale, the delivery of the order arrives today, it shows up instantaneously on the shelves. That's an assumption. Okay, it shows up in our inventory immediately. There is no lag. Also, if this is the level of inventory that is reached every time we place an order, then this area under the graph is represented usually by half of perpendicular times base, okay, which is where the average amount of inventory comes into the picture. Because let's say if you have $5 at the beginning of the month and you have $0 at the end of the month, the average dollar you had over the period of month is 5 plus 0 divided by 2. So either way you look at it, either you look at it from area under the graph, or you look at the average of starting plus ending inventory divided by 2. So the starting one is Q, starting inventory is Q, ending inventory is 0. So you take an average inventory that way. Or if you were to look at half of Q from the area under the graph perspective, that's also the same. Now, the important thing to remember is this half of Q comes handy when you have to calculate the average cost of holding. Because if it costs you H dollars to store 1 unit for 1 year, then average inventory on hand is Q by 2. So if you were to multiply this, this becomes your holding cost, okay, for the year. Now let's solve some of the problems. Before we move on to the problem, let's see some of the formulas that we'll be using. So annual setup cost is the number of orders placed every year times the setup cost of one order. Yeah, so if it, let's say if it costs you $10 to place an order, then the number of orders you placed times $10, that will be your total annual cost of placing the order. Now this is the annual demand in D. Number of units in each order, let's say if you were to divide that, you will get the number of orders placed. Yeah, so number of orders placed is the annual demand divided by the number of units in order. So this is like if you consume 1,000 beer bottles in a year, every time you go to the gas station, assuming you're buying it from there, and there are 6 packs, then the number of times you end up going to the gas station is 1,000 beer bottles divided by 6 pack. Okay, that is how many times you ended up going to the gas station. Now let's say if the cost of going to the gas station is 50 cents, then the annual cost of purchasing the beer is D by Q times S. Okay, now just trying to break down as to how you can remember the formula. And then the next one, this I already showed you on the graph, the average inventory level is half of Q. Okay, half of Q times the cost of storing 1 unit per year, holding cost per unit per year. This is very important. In the questions, sometimes this cost could be given for a daily basis or a weekly basis or monthly basis. You have to bring it to the level of annual level. Okay, now let us calculate let's calculate some of the problems to get our hand on this. Okay. We have an example here. Let's say the problem number 12.5, wherein we have the stock workbooks. Okay, stock workbooks. Let me read the. So now for the question that we have, we are given the stock workbooks with the following characteristic, when the annual demand is 19,500 units a year. So this is D. Ordering cost for placing one order is $25, and the holding cost, which is like the cost of storing one workbook for a year, is H, is given to us. Now if we want to calculate what is the optimal amount of quantity for the workbooks to be ordered such that our ordering cost and holding costs are minimized, then the first thing we want to calculate is, formula we know, the square root of 2 times D times S divided by H. Now a lot of times people do a mistake in the order of multiplication and division. Okay, so please take this into account. Where you place the parenthesis will make a difference in your calculation. Okay, so the first thing we need to do is, in order to take a square root, first I want to calculate this number itself. So I should correct this so then there is no confusion there. Oops. Okay, so first I'm going to calculate start of parenthesis 2 times D times S divided by H. Okay, so in this case there is less likely to do any mistake because there's no addition or subtraction in this calculation. So that gives you this, and then either you take the value that you just calculated and then hold shift, press 6, that'll give you the raised to the power sign, and if you were to say 1 by 2 or 0.5, that would give you the square root. If this helps you, this method of putting in the raised to power helps you do the square, the cube, and also take the under root or the square root. Or there's a special reference for taking square root of the number and then close the parenthesis, SQRT, and that will also return the same value. So whichever method works for you, or if you like, it's one and the same thing. Okay, so now we know the optimal optimal amount of quantity to be ordered is 493 workbooks at a time. How? Because at this point the cost of holding would be this divided by 2, which would become your holding average inventory level. Okay, I should do this someplace else. Let's say this divided by 2, and it costs you $4. Yeah, it costs you $4 to store one workbook. Therefore, storing 246 workbooks for a year will cost you $987. Also, the cost of placing the orders. First, we need to calculate the number of orders, which is the annual demand divided by how many units are we placing in single order? 493. Therefore, the number of orders we ended up placing is 39.4 orders annually, and one order costs you $25. Therefore, 39.4 number of orders will cost you 987. Okay, now I recommend not rounding up unless that is the end calculation. You see, if you were to round this up from 493 to 494, your end values here will change, correct? So try not to round up the values unless that is the last calculation that you have to show in. Okay. So let me show it to you, 494. So see that? So it's better not to round up anything. Now at this point in time, the cost of holding holding or the cost of storage is exactly equal to the cost of placing the order. Now this is not only based on the assumption of the EOQ model, but also that's how we derive the formula that we are using here. So if you're using anything related to EOQ, one way to check yourself is that your cost of holding and ordering has to be equal. Okay. Similarly, now that we know, you can again calculate. This is another example. Henry's law office has traditionally ordered ink refills 60 units at a time. Okay, so in this case we are given the EOQ essentially. Okay, the firm estimate that carrying cost is 40% of $10 unit cost. So few things that we are given here is let's see. Oops. Come on. No? Okay. I'll do it like this. Okay. So now in this case, EOQ is given to us as 60. Holding cost is given to us as 40%. Come on. 40% of $10, which is 40 cents. Yeah. And what other information is given to us? Assumption of EOQ are thought to apply. For what value of ordering cost would this action be optimal? Okay. So let's see what all things are we given. Now EOQ is 2 times D times S divided by H. Okay. Not the last one was not good. Okay. Yeah. Now in this case we are given 60 as the EOQ. Annual demand is 240. So 2 times 240. Setup cost we don't know. This is given to us as 40% of $10 is $4, not 40 cents, sorry. And the square root of this is equals to this. Now when you want to solve for S, you'll end up squaring on both sides, so that'll become 3600. This will come on this side, and this will come on this side. 36 times 4. Why is this decimal there? This is 40% of $10. Yeah, so that'll be $4. That's what it's here. Okay, so 3600 times 4 divided by 2 times 240. This would be the setup cost. So ordering 60 refills at a time would be only good if the cost of placing the order was to be this. So 2 2s are here, and then 6 6 are 36, 6 4s are 24. This is what we're left with. Then 2 20, and then 0 goes here, 30. So we come back to a 30. So as long as the setup cost is $30, it is good to place 60 ink refills at a time. Okay, so in order to answer for what value of ordering cost would its action be optimal, that's $30. If the true ordering cost turns out to be much greater than 30, what's the impact on the firm's policy? So if the cost is to be much larger than 30, that means the optimal order quantity would be proportional to the square root of this increased value. So let's say if the cost of this was to be by increased by how to say, let's say it goes to 90. Theoretically it would be easy if I was to give you an example of 900. If it was to go from $30 to $900, then your EOQ is likely to be increased by a significant amount, or which is exactly the square root of $900, which will be 30. So your EOQ would be multiplied by 30 right there. Now I'm just giving you this huge increase because it's easy to take a square root of 900, which is 30. Yeah. So to answer this question, every time you increase the setup cost, the square root of that would be what is going to affect your EOQ. So let us calculate this in here. EOQ is given to us as 60, 40% of $10, so equals to 0.4 times $10. So that's your H, and your annual demand is 240. Annual demand is 240. So first thing I want to calculate is the square of this. 60 shift 6 raised to the power 2. So now I have EOQ, D, and H. Now I can calculate for S. Yeah. So S would be equals to, now I'm going to be very careful about the parentheses, okay? 3600 times 4, 3600 because I've already squared the 60, okay, and then rearranged it. What happened here now? Okay, apparently it vanished. Okay, never mind. So divided by, okay, divided by 2 times, let me put parentheses here, 2 times 240, okay, and at this point I should get my setup cost in dollars values. Okay, now let's see what happens, as the question was, what happens if the true ordering cost turns out to be much greater. Okay, now if the ordering cost was to be much greater, then we can say 2 times D times S divided by H raised to power 0.5. So if our ordering cost goes to 900, then our optimal order quantity also goes up. Now let's say if this, instead of 30, it goes on to 60, then what happens? The optimal order to place is 84 ink refills instead of 60. So that way, just wanted to show it to you. Now the next one is where in this case we were told everything is discrete and given, there is no change in there. Okay, now let me highlight these answers. Okay, we are given the annual demand, the holding cost, ordering cost, company that operates 300 days a year, the lead time is 2. Okay, so in this case everything was given at one instant. Now we are introducing the concept of lead time. Lead time is the time you place the order till the time the order shows up in your inventory. Okay, again, we are making those assumptions that there's no breakdown time and so on. So if you were to look through your PowerPoint, lead time is Control-Shift-D. So let's say when the order was when the order showed up in the inventory, the last order, your inventory level was here. Now at some point you place the order such that the consumption is being made going on at a constant rate. Yeah, that's why this is a straight line. In reality, this is never a straight line, because it rarely happens when your inventory is being depleted at the same rate. Now let's say you place the time, you place the order, and then your order shows up, which is shown here, yeah, in the inventory, just when your inventory reaches 0. Now this is just to introduce this concept. At some point you would always want to place this reordering point such that when the order shows up, yeah, when the order shows up, you still have some level of inventory. This is called as a buffer or a safety stock, yeah, because what if the depletion rate was to go higher, your inventory would go down faster. Okay, yeah, okay. Now let's see how does that affect the things we need to take into account. Lead time or the depletion rate would become your the rate of consumption in shorter amount of time. So if somebody is working 300 days in a year, you would divide the annual demand by 300. Okay, so, and also you also have to take into account the reordering point is that the depletion rate for the shorter duration times the number of days it takes for the order to show up. Okay, now the next concept that we need to know is that the consumption is happening at the same time when the production is happening. So if, let's say, you make 10 cookies per hour, but you consume 2 cookies per hour, your net addition is 8 cookies per hour, correct? So at the rate of 8 cookies per hour, you keep on making, let's say, for 5 hours, then you stop. So in those 5 hours, you have added 5 times 8, which is 40. So let's say you reach the level of maximum level of 40. After that, you stop producing, but you kept consuming. Okay, so those 40 would last you for next 20 hours because you're consuming 2 cookies per hour. So at the rate of 2 cookies per hour, these 40 would last you for the next 20 hours. Okay, so it'll last you for 20 hours. Then you start doing the same. You start making 10 cookies per hour, but you keep on consuming 2 cookies per hour. Your net addition is 8 cookies per hour, and by the time you reach the maximum level of 40, then you stop producing, but you keep consuming at the rate of 2 cookies per hour. Yeah, so this is the production and depletion example. The example when the production and depletion is happening simultaneously. Now, one thing, the way your formula changes is only with the holding cost. So this, instead of looking at this as a new formula, if you were to look at this, this is nothing but D minus P over P. So this is depletion minus, so this is P here, P minus D divided by P. This is the only ratio that gets added to the holding cost. Yeah, so everything else remains the same. This is also maximum inventory level. Instead of Q gets multiplied by production minus depletion. So the production was your 10 cookies. Yeah, depletion was 2. So it's nothing but the ratio of 10 minus 2 divided by 10, which is 8 by 10. This is the ratio that gets multiplied to everywhere that we were using so far. Gets multiplied to the Q, that's the maximum inventory level reached. So if you made these cookies for about 5 hours, where was I? Yes, here. So the maximum inventory level reached times holding cost, that would give you your holding cost. So initially our formula would have been half of Q times H. Now we have to multiply this old formula, yeah, by P minus D by P, which is nothing but the ratio of production minus depletion divided by the total production. Now what is production minus depletion? This is the net addition. Yeah. So in the formula, when we made 10 cookies, but we ate 2 cookies per hour, our net addition was 8. So net addition divided by the overall production, that's what the ratio is. Okay. Now if you were to look at our original formula, again this and this is the same. The only difference is that H needs to be multiplied again by 1 minus D by P. Now it is recommended that you calculate this number separately in Excel, because at this point the order and the parenthesis will make a huge difference in the calculation. Okay. So now let's look at some of the examples here. Okay. First thing is, we are given annual demand. Holding cost is given to us, and ordering cost per order is given. Company operates 300 days, so the lead time is 2 days. So first thing is, if annual demand is 15,000, it operates 300 days. So using these two, we should be able to calculate the daily demand, which is 15,000 divided by 300. That should give you the daily demand. This is our small d, also called as depletion rate. Yeah. So first things first, what is the EOQ? Okay. So remember, we have our formula 2 times D times S and so on. So let's use that. So let's first calculate what is the optimal order quantity. I'm going to say equals to 2 times the annual demand times the setup cost divided by the holding cost. Okay. And equals to the square root of this, shift 6 raised to power 0.5. So we should be placing 300 units in single order. At this rate, our average amount of product in the inventory would be half of this. So the ordering cost is 150 times 25. Also, the number of orders we'll end up placing is annual demand 15,000 divided by 300. So we'll end up placing 50 orders, but one order costs us $75. Therefore 50 times 75, that gives us 3,750. Now oops, dollar values. Okay. Now if lead time we are given is 2 days, yes, so this is like, if I'm placing an order on Amazon, it takes me 2 days to deliver, then when should I place the order? Okay. Now our daily demand, which we got by annual demand divided by 300. That gives us daily demand of 50 units. Now, 50 units are sold or depleted in one day. So if it takes 2 days for the order to arrive, we should have at least 50 times 2, which is 100 units on hand when we should place the order. Because when you place the order, first 50 will be good for day 1, the next 50 would be good for day 2, and on day 3 you will have the order of 300 that you just placed. Okay, on the third day you will have 300 showing up in the inventory. So let's calculate that here. So, and just to refresh, our reordering point is the daily demand times the lead time. Yeah, so reordering point is daily demand times the lead time. So it would be easy to calculate here, equals to the daily demand times the lead time. So the reordering point is when there are 100 units in the order. Okay, now this can be based on number of kaizens, wherein the moment the inventory level reaches 100, something should trigger the order, the placing of the order. Okay, it could be either automated by the software, or anytime you do the cycle counting of the inventory and you find out the level has reached 100, then you immediately place the order for 300 units. Okay, now let's look at the next concept. Now the next concept we have is when the production and depletion are happening simultaneously. So we have the race 1 car motors that is producing at the rate of 300 units a day. It uses these subcomponents at the rate of 12,500 per year for 250 working days. So a daily production rate would be 12,500 divided by 250. Holding cost is $2 per item per year, so that's our holding cost. Setup cost is $30 per hour. First thing, what is the EOQ? How many production runs will be made? This is similar to how many orders do you end up placing in a year. What is the maximum inventory level reached? Now, okay, now before we calculate, let's review what we need to know for this. Yeah, if you remember, this is the concept. So the production is happening and depletion is happening simultaneously for a certain time. Then the production stops. So this level here is what the maximum production level reached. It is being produced. Let me get rid of this. So this is the information given. So the production is happening. Production is happening at the rate of 300 units a day. Depletion is happening at the rate of 12,500 divided by 250. This is the depletion rate, or the consumption. Holding cost is given to us as $2. Ordering cost is given $30. And now the question is, what is this inventory level, the maximum inventory level reached? And then which is here, how many production runs will be made, which is equals to how many times. This is order 1, order 2, order 3. So how many such production runs will be made, because every time an order is placed, a production run happens, but it may not happen all the time. It happens only till the time when the inventory level reaches a certain point, and then only the consumption continues and the inventory level goes down. Now again, at this time we are assuming that all the consumption is constant. Yeah, so this depletion rate is constant. It never changes. Every day it's the same. Then what percentage of the time will be the facility will be producing? So if, let's say, this thing happens for 2 days, such that the next 8 days nothing is produced, only consumption is being done, then we can say 2 divided by 2 plus 8. So the production is done 20% of the time, and then the usual thing, what is the annual cost of ordering and holding the inventory. Okay, so let's solve this. So the first things first, in order to minimize the mistake, I've broken the calculations down here. So let's see if we were to do calculate EOQ equals to 2 times the demand, annual demand is given to us, times the setup cost. Okay, now this is the numerator part. Yeah, the denominator part, before I do all of this, I'm going to calculate the D by P only. So the depletion rate, let me calculate the depletion rate. Oops. Depletion rate is 12,500 divided by 250. If so this is the depletion rate, and then the depletion by the production rate. Now production rate is given to us as 300 per day. Okay, therefore 1 minus equals to 1 minus D by P. That's 1 minus D by P. Okay, now this would be same as if you were to do P minus D divided by P. Remember, if you were to do P minus D divided by P, in that case also you will get the same number. Production is 300 minus the depletion divided by production. Okay, nope. Okay, I don't need this last parenthesis. So however you do this, if you have however you want to reach, if you want to take baby steps, all that matters is that you have to be accurate. Okay, so now we know 1 minus D by P, therefore holding cost of $2 times the function 1 minus D by P. Yeah, that gives us the denominator part. So therefore at this point I would say numerator divided by denominator. So 2ds divided by h times 1 minus D by P is 450,000. At this point I can say square root of this number. So the ideal amount of inventory that is reached, the maximum level inventory reached, is 670 units when the production and consumption are happening at the same time. Okay, now we know what the annual demand is, yeah, divided by the EOQ that we just calculated. This is how many times the production run was started. Okay, so let me show you. So at this point what we are saying is I want to see this as well. Oops. Come on. So what we are saying is that at this point we reach the level of 670.82. However, since the annual demand is given to us as 12,500, therefore the number of production cycles is 18.6. yeah, so there would be 18.6 such triangles over the whole year, given the fact that they work only 250 some days in a year. Okay, now let's move on to the next question, next part of the question. Yeah, the next thing we are asked is So the maximum level of inventory reached would be Q times equals to Q times 1 minus D by P. Okay. So even though they produced 670 units, the maximum inventory level reached was only 559. Okay. Now let's understand this. So at this point, the total production that happened was 670 units. But because they are also consuming at the rate of 50 units a day, the maximum level reached was 559.02. Yeah. Now this is happening because while the production was happening, the consumption was also happening. Okay. So let's move on to the next part of the question, which is what percentage of the time facility would be producing components. Okay. Now at the rate of production of 300 per day, with the maximum production needed 670, they would not be producing all the time. They would only be producing certain time of the year. So if they can produce 300 units a day here, so if they can produce 300 units a day, how long will it take for them to produce 670 units? It's 670 divided by 300. That should give you the number of days it takes them to produce at the rate of 300 units a day. Okay, so the number of days it takes them to produce 670 divided by 300, so it takes them 2.23 days to get to the maximum level of inventory of 59, while 50 units are consumed a day. Okay, and the days of consumption only would be how long it takes for them to finish this maximum inventory level reached at the rate of 50 units a day. So if they consume 50 units a day, this 559 would last them 11.18 days. Okay, so let's understand at this point what we have here. So at this point, what we are saying is they produced 670.8 units ideally, and they reached the level of 559 some units. It took them 2.23 days to produce, to reach this 559 level. Then at the rate of 50 units a day, it will last them 11.18 days. Yeah, so the total time would be sum of total time from here to here would be 2.23 plus 11.18, and then you can also calculate what time was the production being done by doing 2.23 divided by 2.23 plus 11.18. That would be the percentage of the time when the production was happening. Okay, now let's calculate what is the next thing. What is the annual cost of ordering and holding the inventory? Okay. Oh, and I forgot. So the percentage of the time facility is producing is equals to 2.23 divided by this plus the consumption only, and that's in percentage format. The cell is already formatted for percentage, so it's 16% of the time the production is happening. Now the next thing is, what is the cost of ordering and holding the inventory? Okay, so the cost of ordering would be number of orders times the ordering cost. So the number of orders we've already calculated, 18.63 times the ordering cost. Now, remember, since we are still using the EOQ model, our holding cost should come out to be the same as the ordering cost, just as a cross check. Now, the inventory cost would be whatever the maximum level that we reached. So the maximum level we reached was 559. Yeah, so half of that is what stays in the inventory all the time. So if we reached 559, so half of that would be somewhere here. That's the amount of inventory that was in the store all the time, but it costs us $2 per item per year. So the inventory cost would be 559 half, and then whatever that is, multiply that by 2. Okay, so let's say equals to the maximum inventory we reached divided by 2, and at this time I'm going to multiply it in the numerator. Okay, so let me do this over here again. Equals to 559 divided by 2, and then this number needs to be multiplied by the storage cost of 1 unit for the whole year, which is $2. Okay, so the total cost of ordering and holding cost would be this plus this. Okay, now this, all these costs are in dollars. Control Shift dollar. Okay, so that's the example when the production and depletion are happening at the same time. Okay. Okay. How many bats? So one way to do this is we go to the end of it where we are given the appendices. So at this point we can calculate or read our table for the z-scores. So at this point this is using appendix 1, wherein we are given the area under the graph in the table. So if you were to look for 98%, 97, 98, so this is the first value closest to 98%. So if you look at the column, it's 2.0. The next 10th decimal given to us is 0.06. So at z of 2.06, we get 98% of area under the graph covered, and that is the service level that we want to maintain. Okay, so either we read it from the table like this, okay, the z-score of 2.06 corresponding to 98% service level, or we can also calculate it. So first let me write down 2.06 somewhere. So from the table we get 2.06. Yeah, now, or we can also say, let's say tomorrow if you don't have the z table nearby, then we write down the service level desired in percentage, 98%. Then the way you can calculate z is using normal standard deviation inverse, norm S inverse, and then you refer to the probability, okay, and that'll give you your z-score, which is a lot more accurate. Either way, the z-score should be close, very close, okay. Therefore, the standard deviation, well, standard deviation is given to us, right? So standard deviation is given to us as 100, and square root of lead time. Therefore, now we can do the z times the standard deviation of the demand. So z we know, 100 we know, standard deviation of the demand we know, and the square root of lead time, which is 2. Yeah, so now we can multiply all these three numbers, equals to z times sigma of demand times the lead time. Okay, now this 290 towels is the safety stock. If the demand was not to fluctuate, or if the hotel was not worried about running out of stock, then 1,000 towels a day, and with the lead time of 2 days, it would have been sufficient to carry 2,000 towels on any given day when they place the order for the linen company to come over, because 1,000 towels would be used on the day 1, and the next 1,000 towels would be used on day 2. But in addition to these 2,000 towels, they need to carry 290 some towels, such that even if the demand was to be on the higher end, because this is at the rate of only 1,000 towels, 1,000 guests coming in per day. But what if on some days there were to be more guests on the upper end, which means on that day more towels will be consumed. So they need to keep 290 more towels that will allow them to cover 98% of their demand. Yeah, remember 98%, this was reflected by the z-score. Yeah, so 98% of the time they would have something on hand, and that can be reflected by carrying 290 more towels on hand. So this is what we call as our safety stock. Okay, so the reordering point theoretically should be the demand during the lead time, okay, which is 1,000 times 2 plus the safety stock. Okay, so the reordering point for the linen company should be when the inventory level reaches 2,290 towels in the hotel. Okay, so this is what we already covered. When the demand is variable and the lead time is constant. The next thing could be when the demand is constant but the lead time varies. Yeah, so let's say instead of that linen company here, instead of taking 2 days, it has its own. So there's no standard deviation, no variation in the demand. But instead, the linen company says we might come in somewhere between 2 and 3 days or 2 and 5 days and so on. In that case, we need to be accounting for the variation in the lead time, or both of them might change. The one thing you have to remember is that the standard deviation cannot be added. So this is coming from, if you remember from the chapter of project management, if you have the standard deviations for the demand and you have the standard deviation for the lead time, they cannot be simply algebraically added. That is wrong. Instead, the square of these, which is the variances can be added. Yeah. So if you were to let's say square each of them, then that becomes variances. Now the variances can be added. Therefore, the resulting standard deviation can be calculated by the square root of sum of the squared standard deviation for the demand and the lead time. Okay, that's how this formula comes into the picture. Okay, so moving on, we also have a single period model wherein only one order is placed for the product. In this case, this formula helps you to calculate is what is the service level that can be achieved given the lost sales and the cost of overage. Okay, so let's calculate. Let's practice one of the problems like that. So we know the question. Let me give you the full version. So given the full version of the question, it says Cynthia Knott's has an oyster bar wherein she has a cost of purchase at the rate of $5 per pound and sells them at $9 per pound. If she cannot sell them, then she gives it to a nearby cousin or a friend at the $2 per pound. Yeah, so this is she's selling it to cousin. What a nice way to be. Okay, anyways. So the first thing we have to calculate is the cost of shortage. So let's see the cost of shortage. If you were to be out, then it's sales price minus the cost of purchase. So that's the cost of shortage. So the sell price minus the purchase price. Yeah, simple. No complicated calculations. And then the cost of overage would be if she purchased too much, then the buy price minus the salvage value. This is what she can retrieve. This would be same as if you were to purchase a whole lot of magazines and then you have to sell them by a pound for recycling the paper. So it will be 5 minus 2, that's 3. Now the service level, that is calculated by the cost of shortage divided by the cost of shortage plus overage, which can also be looked at the ratio of cost of shortage divided by the total cost. Okay, this ratio determines how much people would order or how much they should order. In terms of percentage, it gives you an idea. If this percentage is higher, people or the business will tend to order a lot more in order to maintain higher customer service level. Why? Because the cost of shortage is higher compared to the total cost. If that's the case, even if there is a lot of waste, in order to maintain higher customer service level, you will tend to order a lot more. Okay, now this was just on a side note. Let's come back here. So the cost of shortage is given to us. We calculated this. Cost of shortage divided by cost of shortage plus overage. So that comes out to the customer service level of 57%. Now, if given these prices, she's okay with, like she as in Cynthia, is okay with the customer service level of 57%, which means 43% of the time when the customer walks in, she is out of stock. Also, at some other times, she might have too much and she may need to sell it to the cousin. Now, it is also given in terms of information that the demand follows normal distribution, a mean of 100 pounds and a standard deviation of 15 pounds. Okay. So first, let us calculate what this service level means in terms of the standard deviation for the demand. So last time we used norm S inverse. This time we will use normal S distribution for the service level. Okay. Oops. So let me fix this. What did I do wrong? Okay, I misspelled this. So equals to norm S dist. Okay, so that amounts to hold on. So this 57% norm S INV corresponds to 0.18 standard deviations from the mean of 100. So now we want to find out if one standard deviation is 15, then how many standard deviation will this 0.18 be? Okay. So we are given one standard deviation is 15, but we want to be 0.18 times standard deviation away from the mean. So this is a safety stock. So the total she should order is equals to 100 plus 2.7. Now, since this is the last calculation, we can say that she should order 103 pounds. Okay, and so at this point, it's okay to round up because this calculation is not going to be used by anybody else or later down in the calculation. So I think that's about all the various types of problems that can be there in the inventory management. If you guys have any questions, feel free to contact me. I hope you enjoyed the chapter. Thanks. Bye.